History is usually told through the rise and fall of great empires, right? We memorize the names of powerful kings and the dates of these huge, sweeping battles. But, well, beneath the surface of all those stories, there's actually a much deeper, far more fundamental evolution going on. It's this mysterious, almost hidden, systemic thesis, the story of how humans looked at the natural world around them, just ordinary wood, stone, and fire, and somehow transformed them into highly complex systems of power. Welcome to This Explainer. Today we're going to trace an incredible cinematic journey, from the very first stone picked up on a prehistoric savanna, all the way to the armored machines that crossed the muddy trenches of the Great War. We're going to see how our ancestors didn't just find tools, they built complex machines.
Okay, let's dive into this by defining our core concept for today, the engineered system. You see, the central revolution in human history wasn't just in, discovering new materials out in the wild. It was in the engineering itself. An engineered system is the deliberate transformation of nature into mechanisms that do three absolutely critical things for us. First, they extend our physical reach. Second, they store our muscular strength. And third, they precisely control the release of energy. So we're going to look at the very first tools through this exact lens and really examine how human power itself became an engineered system.
Section 1. The Genesis of Reach. Now, you might be wondering what the first weapon was, but archaeology actually can't point to a single definitive first. But I want you to reframe the beginning of human engineering here. Don't think of it simply as our ancestors just stumbling upon tools by accident. Frame it as a highly deliberate, conscious attempt to solve the strict physical limitations and the very real daily risks of survival. To survive, early humans literally had to engineer solutions to keep danger at a distance. But to understand this early engineering, we have to talk about what archaeologists actually dig up. We call our earliest era the Stone Age, right? But that name is massively influenced by survival bias. Stone survives for millions of years in the earth, but wood, fiber, hide, they decay almost immediately. Because of this, the Stone Age is named after what lasted, not necessarily what humans use the most. To put that into perspective, researchers at Schöningen, Germany, discovered 400,000-year-old wooden spears right alongside the butchered remains of more than 10 horses. Long before these spears were left behind in the dirt to be discovered by us, our ancestors were masterfully engineering wood to thrust from a safer distance. They were turning a simple branch into an engineered solution for the hunt.
For hundreds of thousands of years, a weapon's power was strictly limited by the speed and the raw strength of the human arm holding it. But then came this revolutionary engineering idea: energy storage. The bow was not just a longer-range spear, guys, it was an ancient machine. By bending flexible limbs, a person applies force. They store elastic energy, which is essentially just tension held in check, and then they transfer it instantly to the projectile. With this ancient energy machine, applying force and then actually releasing it became two completely separate moments in time. Reach was no longer just about the physical length of a wooden pole. It was now about the physics of stored power.
Section 2. Forging industrial metal systems.
So as human societies grew larger and naturally more complex, so did their needs. They suddenly required standardized, repeatable technology that could be produced at scale. And this brings us right out of the realms of wood and stone and into the era of metal, where engineering takes a massive, massive industrial leap forward. Think about it. Stone tools were shaped individually by hand, meaning every single object was entirely unique. But the invention of bronze casting completely changed the game. It introduced the incredibly powerful engineering concept of repetitionality. By pouring molten metal into a single mold, craftspeople could reproduce identical, complex designs again and again. But here is the thing to remember. Bronze wasn't just a stronger material, it was an entire industry. Copper and tin are rarely found together in nature, so to even produce bronze in the first place, humans had to engineer these massive, fragile, long-distance trade networks, specialized workshops, and a system of highly organized labor.
Now, what's really interesting about this slide is that there's a massive historical myth we need to debunk right now. It's a super common misconception that early iron replaced bronze because it was instantly, magically superior. No way. In reality, early iron was absolutely not automatically stronger than high-quality bronze. The real shift was actually in system accessibility and labor. You see, bronze relied on this system of rare materials and fragile trade networks that spanned thousands of miles. If a war or politics disrupted those routes, well, the whole system just collapsed. Iron ore, on the other hand, was accessible almost everywhere. Unlocking it just required a totally new system, immense amounts of heat to forge it by hand, and an entirely new class of highly skilled labor. So the material itself didn't change history, the system that produced it did.
Section 3. Physics and stored power.
We've seen how humans manipulated materials, but the next massive leap in engineering involved finding ways to mechanically hold power ready. Human endurance has very strict limits, and as societies built these towering stone walls to protect themselves, engineers basically had to figure out how to pit physics against stone. Just think about how your own arm shakes when you're holding a heavy weight for too long. The standard bow released energy instantly, sure, but it required the archer to hold all that physical tension with their own muscles until the absolute perfect moment of release. The crossbow mechanism brilliantly solves this physical strain. By adding a rigid stock and a mechanical latch, this system completely separated the stages of use. You store the energy, the rigid latch holds it ready, and then you just aim and release. This mechanical system could hold heavy tension for hours without a single ounce of human effort. It was a masterpiece of precision craft that controlled stored energy perfectly.
Let's move to and see how this builds when these handheld machines met the towering stone walls of medieval fortresses. Engineers basically had to scale up. They turned to massive siege engines like the trebuchet or the ballista. Now, these weren't just big weapons. They were entire logistical systems. They used the absolute physical limits of tension, torsion, leverage, and gravity. Just operating them required a vast mobile industry of craftspeople and the highly coordinated transport of massive timbers. It was an entire system pitting the raw laws of physics against static stone fortifications.
Section 4. The architecture of gunpowder.
But those static stone fortifications were about to face an entirely new crisis. The arrival of gunpowder literally forced humans to completely redesign the very architecture of their cities. Traditional medieval walls were tall and thin, which as it turns out made them absolutely perfect targets for heavy cannons. And this brilliantly illustrates how engineers responded. They turned the fortress into a geometric machine. They lowered the walls to keep them out of sight, they made them incredibly thick, and they backed them with tons of earth to just absorb the massive kinetic energy of a cannon strike. Furthermore, they used these angled bastions to completely eliminate blind spots. The fortress was no longer a simple static barrier. It was now a highly complex, geometric system of interconnected zones of fire.
While cannons completely reshaped architecture on the outside, engineers were facing a different, incredibly meticulous problem on the inside of the weapon itself: how to control the spark. Early gunpowder weapons relied on this really clumsy external ignition. What followed was literally a centuries-long engineering quest to dependably integrate and control the exact moment of ignition directly inside the weapon's mechanism. We went from the smoldering cord of the matchlock, to the intricate, almost clockwork friction of the wheel lock, to the sparking stone of the flintlock, and finally to the chemical reliability of the percussion mechanism. It was just a relentless pursuit of controlling exactly when the power began. But ignition was really only half the battle. Accuracy was the other. For centuries, barrels were perfectly smooth on the inside. Then engineers discovered that cutting spiral grooves inside the metal barrel could impart a spin to the projectile. So the crucial point is that rifling didn't create more explosive energy. It engineered a way to perfectly control how that energy moved through the air. This controlled spin created rotational stability, basically turning the chaotic, tumbling flight of a projectile into an engineered, predictable certainty. A real game changer for sure.
Section 5. Engineering the modern machine.
We now arrive at the 20th century, a time of truly unprecedented industrial scale. By 1915, the landscape of the First World War had become a horrific engineering nightmare. The muddy, cratered trenches literally stopped ordinary wheels dead in their tracks. A massive crisis was at hand, and it demanded an entirely new system of mobility. The solution they came up with was to combine continuous tracks, mechanical engine power, and armored protection. I want to guide you through this specific, rapid evolution because it's fascinating. It started with Little Willie, the very first working prototype. Now, Little Willie proved that a tracked engine could move a protected structure, but it was really just a moving experiment that never saw actual combat. Testing its physical limitations directly led to a second prototype known as Mother. Mother introduced that iconic rhomboid shape you've probably seen, specifically designed to better cross wide trenches. And that design became the foundation for the Mark I, the actual first tank to enter production and roll into combat in September 1916. The first tank was not a finished, perfect answer. It was a massive industrial system of mobility born out of a literal crisis.
We have traced an absolutely incredible journey today. We have moved from natural objects to elastic energy storage, from the repeatability of bronze casting to the ignition control of gunpowder, and from flight stability to protected, mechanized mobility. In every single age, the question was always exactly the same. What physical problem must engineering solve next? From stone held in the human hand to armored machines moving on tracks, weapons changed whenever human power became an engineered system. This was weapons that changed history. But as we look around today at the AI and autonomous systems being developed for tomorrow, we have to ask ourselves one final slightly chilling question. Are we still engineering the weapons, or are the systems finally engineering themselves?